it snowing a lot where you're at?
No, we got a little bit of a dusting, but that was a bit. I can see that there's more snow up in the La Salle Mountains. That's pretty high peaks up there, over 12,000 feet. So they're getting pretty snow capped, and they're covered in snow right now. I hear that they're getting a lot of snow. I haven't been up there; I haven't had a chance. But no, down here in the valley, pretty much nothing in Moab. A little bit of rain, but a little freezing rain, but that's been about it. I see that you're getting some weather up there in Salt Lake City.
About a foot.
Wow. Okay. Well, good luck, everybody. Getting your places shoveled if you have to do it, and lucky you if you don't. So why don't we get started? I wanted to talk today about. Where's my? This always gives me a hard time finding that. Okay, here we go. So, as I show here in this, talking about sections 5.1 to 5.4. Now, there's a section 5.5 that I'm not covering, and that has to do with systems that are unsteady but uniform flow, things like filling a tank or exhausting a tank. Those are not unimportant items, but it's probably something you won't run into, and I've decided to not cover that and instead give you a little bit more information later on in the course in terms of combustion and psychrometrics. So we're dropping off section 5.4, and you'll probably rejoice that, because it is conceptually sometimes difficult for students to be able to get a handle on that and to come back with it on an exam. So we'll just leave that as it is. But I did want to talk about the mass and energy balances for control volumes. Now, a mass balance, if we're looking at a steady state flow, and I have some sort of a device here, and I've got some sort of a mass flow rate coming in, and I've got some sort of a mass flow rate coming out. I'll call that 1, and I'll call that 2. If I specify steady state, what does that mean about the relationship between M1, M.1, and M.2?
They're the same.
They have to be the same. Yeah, they have to be the same. So, my conservation of mass ends up to be really very simple. Conservation of mass is just a summation of everything that is coming in is going to be equal to a summation of the mass fluxes for everything that is coming out. And so if I have some sort of a mixing chamber, right, I could have something here, and maybe I have another tube that comes in, and so if I have like a M1 and a M2, then an M3, then of course M1 plus M2 will be equal to M3, right? So pretty simple summation of masses going in equal to the summation of the masses going out. Now, when we talk about mass, a lot of times we're talking about something that is some duct or some tube or a pipe. A pipe would, depending on the pipe and what would say the Reynolds number, the number which is the ratio of the momentum forces to the viscous forces. If that number is less than like 2,000, we have what's called laminar flow. Laminar flow gives you a particular velocity profile that is parabolic inside of those tubes. And so when we think about the velocity distributions, this is V as a function of R being defined from that center line. So when we think about velocities, we have all of these different velocities that might be happening at different places in these tubes. But in general, we're looking at average values. And by average values, we would say V average. In this case, I just be saying that's an integral from 0 to R times V as a function of R times 2 pi R dr, right? And then I would divide that by the area, which is pi R and pi R squared, right? So what I would normally do is, I don't know if I'd be able to make all of those measurements in all these different places for all the different velocities, but I do know something about what that average velocity would be. And I really don't care about this. If it's laminar flow, turbulent flow, whatever, all I want to know is what the mass flow rate is. I know that the mass flow rate is also equal to my volumetric flow rate times the density, right? So a lot of times when we're talking about like flow in a duct, airflow in a duct, you're going to be given units of standard cubic feet per minute, something in that range, or some amount of volume per time. And then you multiply that by the density. Now, when we say standard cubic feet a minute, it means that we have a flow rate, and then we have to make sure that we have the density associated with that flow rate, which is at standard temperature and pressure, so that I get the mass flow rate, right? So what I'm really after is the mass flow rate. So when I say that volume, standard temperature and pressure, I know what the density is to be able to get the mass flow rate. We also know that that velocity is equal to, or the volumetric velocity is equal to the actual velocity of this fluid that is here, V average, times the cross-sectional area of the tube. Okay, so there are these different relationships that we'd be looking at. The thing to remember here is that if I have a compressible gas, we have to make sure that we have a standard condition so that we can calculate that mass flow rate. But what happens if I have an incompressible fluid? Well, if it's incompressible, then my volumetric flow rate in and out has to be the same, right? So many gallons a minute going in, so many gallons a minute coming back out. So those have to be equal in a steady state system. So, and that's because water is incompressible. Okay, so we have for different conditions, compressible gas. Then you just think of M, and at any time, we can say that this is V average times the density times the cross-sectional area. So if we have an idea of what that average velocity might be, we know the density, and again, that's density, then we can calculate the mass flow rate. So in general, when we're going through the mass balances, we might be given another variable like volumetric flow rate or velocity but then we're always going to want to convert that back to be able to get that mass flow rate, because that's what's constant. That's what's constant through the system, is the mass flow rate. So the summation of all the masses in equal to the summation of all the masses coming out. So that's pretty straightforward. And the only thing is compressible, we have to make sure we're always compensating the density, getting the right density at the volumetric flow rate to make sure that the mass flow rate of that gas is the same. But if it's a steady state process, I can have gas coming in at 1,000 psi and coming out at atmospheric pressure. It doesn't matter about that change in density. The mass flow rate coming in is going to be equal to the mass flow rate coming out by this equation up here. Okay, anybody have any questions on that?
I have a question. For the volumetric flow rate, you have it that equals the V average, which I understand that. What is the AC again?
Oh, that's a cross-sectional area of that tube, right? If it's a round tube, then AC would be equal to pi R. Yeah, that's a lousy R. R squared, right? So we just need to know the cross-sectional area and the volumetric flow rate, and we can calculate the velocity. Or if we had the volumetric flow rate, we're really probably after the mass. And so we just get the density, or 1 over the specific volume, which is the density. And that gives me then the mass flow rate.
What's the integral in the V average equation?
Oh, yeah, let me see if I can clean this up. this term is V as a function of R. Then 2 pi R dr. So what I'm doing is just looking at a ring that goes all the way around the center when I'm doing that integral. So I'm just looking at the velocity times the area, which is 2 pi R dr. So 2 pi R is then the perimeter of that ring, and then dr is the thickness of that ring. So that's a little differential area. So I'm just integrating over the area, the velocity over the area, and then dividing by the total cross-sectional area to get that average velocity.
Thank you.
Okay.
Professor,
Any yes.
should that V, so the V average times cross-sectional area equation, is that V dot, or is that just the basic V?
Oh, I just use V. You know, when I put a dot, this guy here, I try to put this little cross through the volume and a dot over that if it's a volumetric flow rate. And oops, that should be a volumetric flow rate. But in general, you know, the regular V is just velocity. And I try to keep those two a little bit separate. In the book, it is a little bit confusing whether they're talking about a volume or a velocity. So I try to keep that nomenclature different by my velocities having that line through it, and my volumes having that line through it.
Okay, but that should be the volumetric flow rate equals the average velocity times cross-sectional area, correct?
That is correct.
Okay.
Yes. Yeah. Yep. So, you know, this would be meters per second, and then that's meters squared. So that would give you units as meters cubed per second, volumetric flow rate. Or that could be feet per second, and that cross-sectional area could be in, you know, square feet, and then you have cubic feet per second. All right. Good. All right. Let's go to the next. Energy balances. We're going to be saying the same thing about our energy balances. And we can say, put it our energy balances that will look like Wn, some sort of a rate of work going in, plus the rate of heat going in, plus the summation of all the masses coming in, and the enthalpy. I'm going to step back here a moment. I'm going to put this thing called theta in there. Is going to be equal to the rate of work out plus the rate of heat transfer out plus the summation of all the mass fluxes times its energy. So theta is the energy that is coming in with that fluid. Now, that equation is all you need to know, and you should be able to write that down without even thinking about it. Just energy in, energy out. And so once you write that equation down, you can look at a particular problem, and you can figure out, okay, where's my work in, my work out? You can put the right signs to it as you want to define it. But this is really the most general way, and probably the least confusing way. If you stick with this, and if you have an idea of what your system is, if there's work going in like a compressor, you might want to leave it this way. If work going out like a turbine, you might go after this term. In the book, by convention, they say that work out is positive. But you know, it's arbitrary. If you write it in its complete form, you don't need to worry about the sign. Just make sure that if you're defining it as being in, that you're putting it on the correct side of the equation, on the inside of the equation. So that's our energy balance. But you know, what is theta? Well, theta ends up to be our internal energy plus this PV energy plus 1/2 the kinetic energy plus GH. Notice that there is no line through the velocity, right? So that's not a volumetric flow rate. That is the velocity. And so what we're looking at is the potential energy and the kinetic energy and this term here, this PV term. And we've talked about that before. And again, let's just make sure that we understand what that is. If I'm looking at this control volume here, try this new tool. If I'm looking at this control, whoops, I did. That's what I want. Okay. So if I look at this control volume here, and if I'm thinking, well, say my control volume originally incorporated that little block right there. And then with flow, that little block gets pushed in. So if my original control volume came out here, and then it got pushed in, I have a displacement of a P times the change in that volume as it's being pushed in. So not only do I have the internal energy associated with that fluid in here, but I also have that work energy of the flow that has then pushed that fluid into that chamber under pressure. And so I have a PV term that needs to be included into that overall equation. And then, of course, the kinetic energy and the potential energy.
I have a quick question.
Yes.
For your kinetic energy equation and potential energy, why do we not have mass?
Why would what?
Why do we not have mass in our kinetic energy and potential energy equation?
Oh, this is per unit mass.
Okay.
Yeah. Okay, and see, and the mass comes in here, right? So we have the mass flux times this. So this is per unit mass, and then I multiply it by the energy, and then that gives me energy per second, which is then, watts or kilowatts or megawatts or gigawatts, trigawatts, whatever. All right? That answer your question?
Yeah.
Okay.
When you say that, where you plug it back in, do you mean into the summation where there's the mass flow rate?
Yes, where I take this and I just stick it in there. So this would be my that would be my inlet total energy, and this is my outlet total energy. So I would evaluate all the properties here at the outlet conditions and all the properties for my like enthalpy and internal energy at the inlet conditions here. And we know that our value of theta we're now writing as H plus 1/2 V squared plus GH. Now, keep in mind when we're putting in these numbers, typically your H is going to be given to you in kilojoules per kilogram, and your velocity squared, which is meters squared per seconds squared. And if and meters squared per second squared, that is, I'm going to end up with a kilogram meter per seconds. Kilogram meter is a joule, and that gives me joules per second. Well, I need to be getting, this will be, excuse me, I'm kind of messed that up a little bit. Let's go through that again. V squared, meter squared per second squared. And that meters, kilogram, seconds squared. A kilogram meter per second squared is what, a Newton? So what I have is and there's another meter here, kilogram meter per second. And that gives me conditions then of a joules per second, joules per kilogram. Let me make sure I get that cleaned up. So this will give me joules per kilogram. If I do velocity squared, will give you joules per kilogram. But everything else is in kilojoules per kilogram. So whenever you're looking at that velocity squared, make sure you're dividing that by 1,000 so that you're consistent with the units on H. Okay, so basically just wanted to go through this. V squared, units of joules per kilogram. So when you're comparing that to H, which is kilojoules per kilogram, you have to divide that velocity squared by 1,000. And the same thing with GH. They'll give you units of joules per kilogram. Okay, just wanted to make sure that we're clear on that. Although it wasn't very clear going through the units, but make sure that we're clear on how we're making sure that the units are consistent between H and V squared. So what does this mean for different kind of devices? Let's look at a very simple device. And maybe the simplest device you can think of is a throttling valve. In a throttling valve, you have some sort of a pipe, and you have some sort of a valve, and that valve is partway open. So how much work is that valve doing? Nothing. Worthless. It's doing no work at all. How much heat is it adding or subtracting?
That'd be the same nothing.
Nothing. The same nothing. Both of them are absolutely nothing. So in this case, we know that mass N, mass 1 is equal to mass 2. And we also know that the energy N, so we have summation mass N has to be equal to summation out, right? So what about velocity difference? Say probably not. Probably not a lot of velocity difference. There could be, and you can imagine something where maybe there's some phase change, and I'm getting it's going from all liquid, maybe saturated liquid, drop pressure. Now I've got a little bit of vapor, and that vapor is going to accelerate. But no, those velocities are not going to be important because typically the values of H are much larger than what we're seeing on the velocity. Some applications, the velocities can get quite high, and I'll go through one of those applications in a moment. So for this case, m dot in is equal to m dot out, which means that theta in is equal to theta out. And for neglecting kinetic energy, and potential energy, and I end up with H in is equal to H out. So easy, right? All we have to say is, oh, here's the energy coming in and here's the energy coming out, and you've got your system set. Now, for a condition like a throttling valve, anybody know where you're going to find a throttling valve in your everyday life?
Is that what a hose is?
Kind of, I guess, if you're using the length of a hose is to be able to regulate the flow rate. But, I think a really good example of a throttling valve, and we model it as a throttling valve, is that little capillary tube that you have in your refrigeration condition, in your refrigerator. You ever look in there? There's look like a little wire, kind of a metal wire. That's actually a tube. And so what that does, that tube creates a pressure difference from one end of that to the other. And that is treated as a throttling valve. And so in that case, we have what would be coming in would be maybe this would be saturated liquid R134A coming in to the beginning of that capillary tube. And that's meant to drop pressure so that the outlet enthalpy is still going to be the same. What you're going to end up with is a lower pressure. You're going to vaporize some of that R134A, but then you're going in with this low pressure liquid that goes into the evaporator, and it evaporates at a low temperature, which is why you're then getting refrigeration. And it's because of the pressure difference through a throttling valve. And the way we handle it is that the enthalpy coming in is equal to the enthalpy coming out. Okay, so one of the simplest flow through systems you'll run into. Any questions on that? Okay, let's go to some more examples. What about a pump?
Well, in a pump, I reckon you have mass coming in and mass going out, so a little bit different, right?
Yeah. Well, they're all the same in the same mass in and the same mass out. But here we're putting work in. So in the pump, we'll say the work in. We'll say that that's a rate. Will be equal to the mass flow rate. And if I have a pump, and if it's a good pump, it's not going to heat up the fluid, and the fluid is incompressible. And I'm probably across the pump, I'm not seeing a head difference. Well, I see a head difference, but I'm not seeing necessarily a potential energy difference that I'm somehow exploiting. I am creating a potential difference by putting that energy into the pump and increasing its pressure, but that's not showing up directly. Just like a rho H kind of a term. It's more of just a pressure term. So what I have is then theta 2 minus theta 1, and this pump maybe that point there. Okay, so coming in, I've got a mass flow rate and a theta 1. Coming out, a mass flow rate and a theta 2. And I'm saying theta 2 is going to be larger than theta 1 because I'm putting energy in through the pump. Well, there's no kinetic energy change. There's no potential energy change. So what I have, and really if I'm at the same elevation here as here, there is no potential energy change at all. One way of thinking of them. So what I have is H2 minus H1. That's all that's left. And that's equal to my mass flux times the internal energy at 2 minus the internal energy at 1. Plus P1 V, P2 V2 minus P1 V1. Okay, so the difference in enthalpy, U2 plus P2 V2, H1 is U1 plus P1 V1. For no, delta T being equal to 0 gives me that delta U is equal to 0, and V1 is equal to V2. So that work in the pump ends up to be equal to the mass flux times the specific volume times P2 minus P1. Okay? That makes sense? And if I added heat to it, I would put in, add heat onto this side, or if heat was coming off, if it's being cooled, I'd probably, add on the heat coming out to the other side of the equation with all of the out energy terms. Anybody have a question on that? Well, let's look at a term. Oh, yes.
I do. So is that the work rate in equals the mass flow rate times by, is that the
Specific volume.
Okay, specific volume.
Yeah, one over the density.
Okay. And then you would have your pressure 2 minus your pressure 1. Am I understanding that correctly?
Yes, because I'm increasing the pressure, right? So I'm putting that pump in, and the net result of that pump is I'm just increasing the pressure of that fluid downstream.
Okay.
And so that increase in pressure multiplied by the mass flow rate divided by the density, because specific volume is 1 over density. Well, that gives you the work that goes into that pump.
Makes sense. Thank you.
Yeah.
Professor, can you just briefly explain? I think you mentioned it, but where we went from H2 minus H1 to U2 minus U1.
Yeah.
And again,
H is equal to U plus PV. Right? So H2 is U2 plus PV2. H1 is U1 plus PV1.
Okay, got it.
All right. So a turbine. And this is not something you wear on your head. This is a turbine. We use the turbine for terminology on like wind turbines and steam turbines and gas turbines. And so a lot of people call them turbines, but it's the pronunciation is turbine. And the kind of turbines that we would be looking at would be, say, a steam turbine, something you would find in a power plant. And in a power plant, you'd be looking at this turbine where you have some mass coming in and enthalpy associated with this 0.1. And then coming out is that same mass flux times the enthalpy 2. The net idea of a turbine is to have work coming out. And we could have heat coming out. So we'll just put that in, heat coming out. So my energy balance will look like m dot H1 will be equal to W dot plus Q dot plus M dot H2. And M1 is equal to M2. So I don't need to differentiate. They're the same mass flux all the way through. Okay, so say if Q is equal to 0, then my work
Yes,
that
sir?
comes out, yes.
Will we always have an incompressible thing where I guess not incompressible, but can we always say that M1 equals M2 so that we don't have to ever distinguish between the two?
Yes.
Okay.
Yep. Steady flow. Steady flow. What goes in has to come out. Right? That's our definition. I'm reading the basics of the definition of steady flow. The mass fluxes are constant, and the temperature differences or the states at 0.1 and 0.2 are constant with time. Okay? So for this case, Q equals 0, we have a value of work coming out of this is going to be equal to the mass flux times H1 minus H2. Okay? Pretty simple, right? A compressor maybe looks the opposite. And the compressor, I might have some mass flux coming in, and H1 coming out is a mass flux and an H2. And for a compressor, I'm going to put work in at some rate. So my work in is equal to mass flux multiplied by what? Would I expect any change in potential energy? Elevation at that point is the same as that. Kinetic energy, I'm not going to worry about kinetic energy in this calculation. Have to have more information on mass flow rates and the velocity of the tube or the diameter of the tubes and be able to calculate what that velocity would be. If there's no information on the velocity, say just neglect it. Just neglect it, okay? So in this case, we don't see anything about velocity. We're neglecting it. So what is the amount of work that I have to put into the compressor?
H2 minus H1.
Yep, thank you. All right. And if I put heat into it, I would say if I put in a Q, I would just put in a Q there, right? It's just an N. It's just an innie or an outie is the innie. What about a nozzle? Am I putting any work into a nozzle? No, nozzle just a dumb nozzle, right? So how am I going to handle a nozzle? 0.1 and 0.2. What is the purpose of a nozzle?
Increase pressure because you decrease the cross-sectional area.
Well, the pressure you will be, changing your pressure. It depends on the nozzle too. You could have subsonic, supersonic, and it's not necessarily the pressure, but
Maybe velocity, like on a jet engine,
yeah. We're looking for velocity. We're looking for kinetic energy out of that. The higher the velocity, the more force, more impulse we're getting out of that engine, right? So we're looking at change like a DMV, right? Your force. Right. So if it goes from, high velocity to low velocity is like you have a big change in momentum. So what you're trying to do is get maximum momentum right there at that point, and that's going to give you the maximum thrust. Okay. So what do we do for a nozzle? Is it, my nozzle's disappearing. Okay, well, that's an easy thing to draw. Okay, so here's my nozzle. How am I going to handle this? Am I putting any work into it? No. Am I putting any heat into it?
No.
No, just a dumb old nozzle there. So what I do know is theta 1 is equal to theta 2. Elevation is the same, so I don't worry about potential energy, but I do have to worry about kinetic energy, because the whole point is getting kinetic energy, V2, as high as we can get it. So if I look at my overall energy, it is going to be H1 plus V squared over 2 is equal to H2 plus V2 squared over 2. And that gives me the relationship of, maybe move this up to 10, V2 squared over 2 is equal to V1 squared over 2 plus H1 minus H2. And typically for a gas, this H1 minus H2 is going to be a C sub P delta T. And so given the temperature here and given the temperature out there, you have a delta T. And so you can calculate what that delta H would be. Then knowing the velocity coming in, then that gives you a relationship for the velocity coming out. Okay. And so again, for these kinds of conditions, whatever I would give you in terms of a test, an exam, or homework problem, basically you're given conditions to define the state here. That allows you to calculate the enthalpy, and then something here, some state condition here that allows you to calculate the velocity or the work or the work in or work out. So relatively straightforward, and don't let yourself get confused. The only place you really get confused is not identifying that there's a velocity that might be coming into play. The only place that I'll be doing it is for a velocity is nozzles. That's the only place that I really are trying to get a high velocity. Compressors are going to be pretty consistent. You'll be looking at compressors throughout the next few weeks. You'll be looking at turbines. You'll be looking at pumps. And those are just your basic relationships. Really quite simple, quite easy put together. And the problems are going to be the same. We identify the state of the inlet, try to identify the state of the outlet, identify whether we have work going in, work going out, heat going in, heat going out, applying mass balances, applying energy balances, then apply that energy balance to a specific problem, whether that's a pump, a turbine, compressor, a nozzle, or a throttling valve. Okay, anybody have any questions on this? This is really all of chapter 5 that I want you to know. I mean, it's all right here in these few equations. There's not that much. They're just energy balances. Summation of masses in equals summation of masses out. Summation of energy in is equal to summation of energy out. It's that simple. And just a matter of applying those principles to different devices. For the steady state, steady flow, they're all devices: nozzles, compressors, turbines, pumps, throttling valves, you name it. Okay? Any questions on that?
I have a quick question on your notation.
Yes.
Do you differentiate H as height versus H as enthalpy?
Oh, thank you very much for that that point. Yes, H is height. I should be putting that as a Z in my energy term. I really should. So back here, I should put this in as a Z. I'm sorry. That'd be a little bit clearer.
Okay, thank you.
Any other questions?
Professor, can you just explain why on the compressor and turbine we swap the enthalpies, H1 minus H2 and H2 minus H1? Is that just the relationship we're making, that the work that's happening inside of?
It was the direction that we'd assigned our work. So in turbine, the work went out of the turbine as opposed to us putting it into the turbine.
Oh, gotcha. Good. Okay. Thank you, Michael. Okay.
Okay. Any other questions? Well, then we'll call this for the lecture part. Let me finish this off and go back to Zoom. Okay, that's why I can see some of you. Okay, so any other questions? Any other issues to be bringing up? The one thing we all may be thinking a bit about is that we have a exam coming up next Wednesday, and this has been a short week because of taking a little bit of time and slowing down just a minute, let you guys get caught up. I'm going to postpone the homework until Monday. I don't think being a short week. I think you could do it. It's a relatively simple homework problem. I think 5 problems of steady state, steady flow. What I went through today should give you, take you a couple of hours to get it done. But I'm going to postpone that. Make sure that you have plenty of time to get all that down. Over this weekend, I'll be posting a practice exam. I'll just be using an exam that I've used in this class in the past, and I'll be posting, let you work on that. So you'll having homework that'll be due on Monday, and you'll be having that take-home exam that you could be working on, and then we can talk about that on Monday, so you can an idea of what I expect to see on those problems and the kind of thinking that I'm looking for on the exam, and that should do it. I won't have a quiz on Friday. Keep it in mind that we've got a short week and we've got an exam coming up next week. I'll have plenty of opportunity to quiz you on the exam next week, and I don't have to give you a quiz to double up on that. Okay. And Friday we will meet as regular, and we'll be doing some calculations. I've been working on a project, and I've done some interesting calculations over the weekend on some turbines, and we'll go over those calculations. We'll be doing some interesting application of it. Okay, so we'll be talking about a couple of different turbines that are running from a few different conditions, and we'll think about the different performance of those different turbines under different inlet conditions. Okay, and I'll give you some good practice on really a practical kind of a problem thing that literally working on right now to understand some of these thermodynamics. And what I'm doing is looking at energy that's coming from a geothermal system, and we have opportunities to come from different pressures. So, and we're getting steam. So we're just looking, okay, what is the efficiency of steam coming from those different environments? What does that mean in terms of the overall conversion efficiency? Okay.
So is this the last chapter that will be on the exam next week?
Yep.
So just to clarify, that's chapters 1 through 5 on our first midterm, right?
Correct. Okay. Yeah, correct. And you pretty much, the class itself is sort of a scaffolding class. There's a lot of information you need to know. Just understanding how to get around the steam tables is a big challenge sometimes, and understanding how to identify the states and using which relationship for some sort of a pathway and pressure versus volume. There's a lot of those specific things kind of get into your mind to but those are the building blocks. And now that that foundation has been pretty much laid, and with this next chapter, you're pretty much there. And there's going to be a few fun things we're going to be adding on when we get into entropy and exergy and all those kinds of things. But you've got all the basic information to do pretty much most thermodynamic calculations. So anyway, this is really an important part. I want to make sure that everybody gets up to this point and completely understands the material that is there, feels really comfortable doing energy balances, mass balances for closed systems, for fixed mass systems, and for open systems. And it's pretty clear where I want you to be. And I think we're all there. It's a matter of making sure we understand how to get the state variables on inlet and outlet, and then being able to pull values of enthalpy and internal energy and specific volumes off the different charts. Okay. Any other questions?
I do have one question.
Yes.
Will there be a Friday problem still, or does that, because that goes along with the quiz, right?
Well, yeah. There again, there will be a Friday problem. Yeah, and that Friday problem will be the problem that I just talked about of looking at steam that is coming from a geothermal source and looking at the conversion efficiency, how much energy we can get out of that steam for different conditions. And so we'll be working on that. It's, I would prefer that you're there on Friday. It also gives you opportunities to ask questions on the homework in particular.
Oh, absolutely. My wife is actually going to be induced tomorrow night. So I'm going to be in the hospital with her. And so that's why when you said no quiz, I was like, oh, fantastic. If I can make it, great. If not, then there's nothing I'm missing. But if you have a Friday quiz problem, I'll still try to get on if I can. But I just wanted to verify.
And if you have a problem like that, we will get you that in class problem, and we can talk you through it later on.
Yeah.
So, we'll work on it.
I'll email you if there's any issues. So
okay. All right, that sounds great.
I'll send you notes too, Matthew. So congrats for you and your wife, and I'll get my notes and send them to you if it
Thanks,
helps
Francisco.
out. You bet.
Thanks. Yeah, great.
Okay, perfect. Thank you, guys.
All right. Anything else anybody would like to bring up?
Professor, maybe if I can, I'll post a picture on the discussion board. I saw something on the NASCAR Daytona 500 that was pretty interesting, related with thermodynamics. I'll post a picture on there, and but it had something to do with the braking system on these cars. It actually happened on the Tuesday when they were doing all the pre stuff up to the race over the weekend, and it had something to do with as they were coming into an S bend, and they were explaining why this effect was actually happening on it. So I'll see how well the picture came out. I had to take a picture off the TV, and I'll post it on there. And it just
interesting.
I thought about the thermodynamics we were talking about. I was like, oh, that's how they can apply it now.
Yeah. So it's just the braking. So it's catching on fire, too much braking. That really interesting stories about that on, say, the Le Mans. I mean, literally one of the things on the early Le Mans when Ford was really coming into it is that they had a kind of almost a cheat. What they did in the middle of the race, they had their whole suspension system so they could completely pull off the brake, the whole wheels and everything. They could pull that off and slip on a brand new one in the middle of the race, because everybody was just wearing out their race. I mean, they come in at 200 miles an hour, and then they have to make the curve. They're just wearing down their brakes, and you're exactly right. That energy dissipation, the heat dissipation, and it's all just in wear, isn't it? So the innovation was these quick change braking systems that they could pull on and pull off in the middle of the race. It gave them a big competitive edge.
Yeah, that was on that movie, right? Ford versus Ferrari. They had a clip on that. That's a good movie. I recommend that one on there.
Yeah, that was a good movie. And another thing, years ago, probably I'm trying to think, it's probably 80s. there's this controversy about these Lexus automobiles, that their gas pedals were getting stuck to the floor and they were accelerating without stopping. You remember, anybody probably remember that or ever heard of it? Well, it ends up that that's just absolutely ridiculous. So people saying I'm hitting the brake as hard as I can and it's not stopping. That's the most ridiculous thing I've ever heard, because think about it. I can hit my brakes and go from 60 to 0 in how many seconds? 1. Do it over like 150 feet, 200 feet. How could I ever get a car that will go from 0 to 60 in 100 feet, or 200 feet from a stop? Your braking system is so much more powerful than what your engine can ever put out. So much more powerful. And so, when you think about that energy transfer, and when all of that energy you're putting into the energy, that all ends up in the brake, and that brake is incredible in terms of dissipating energy. And you're right, it dissipates it all as heat.
That
off of your
explains
drums.
why what you're saying, there's more energy developed in the brakes, because like when they do the burnouts at the drag races, they're applying their brakes, and even they're revving those engines up. Those brakes are holding that car down. So
I know, the front wheel brakes.
I find that fascinating how that can happen.
Yeah. Well, the interesting thing is what they do is just get that thing in an impulse, and so they just create that kinetic energy, and then it starts to slip. All right. So once you get that slipping, if you have a stationary rubber to road, your friction is much higher than if it's sliding, right? And what they're really doing with those tires is getting that friction so high that they're melting part of that tire, because that'll make it really sticky. So when they're then going to the race, it's like they're literally leaving a piece of that tire on the road as they're coming off, and that gives them the maximum coefficient of friction between that tire and the road. But you're right, it's those front brakes. So it's from the front tires that are getting the braking of all those huge, 1,000 horsepower back there. It's amazing.
Yeah, it's interesting to make the connections now. Once you start getting the connections with thermo, how you can see it now actually happening in real life. It used to be a lot of abstract ideas, but I'm like, okay, now I can make the connections.
Yeah. All that heat that's being dissipated in the brake, that's all kinetic energy. That's the only place it can go. Again, those higher forms of energy, the only way it can end up is going to be in heat. And there's an example. You've got great kinetic energy in your car. You're going to dissipate it in the brakes, and all that energy goes off in heat.
Yeah. Well, that's great. I'll see if I can get that picture posted up on there.
All right. Great.
The class. Thank you very much, Professor Udell. Right. Sorry, I was about 10 minutes late. I had to take my wife to work because she couldn't get out of the driveway with the snow. I've been shoveling snow since 5:30, and she couldn't get out. So I said, hey, I'm going to take you to work, because she works at Research Park. Yeah. And it was just horrendous, the traffic, everybody going slow. But I don't think I missed anything you were explaining when I logged in the energy equation, energy balance. So.
Yeah, the first part was the mass balance. Mass balance, and those are mass. The summation of mass in is equal to the summation of mass out. The one thing that you probably need to know about what I talked about today is that we're not looking at filling tanks. Those transients.
Yeah.
I find that those tend to confuse students, and I'm not sure that that's really needed. It's
yep.
So I'm just skipping over that completely, and once I skip over that,